Okay, so we're going to pick up here where we left off in the second video. Um, and I'm going to save this so I have it, and then I'm going to make a clean copy. So that I keep this separate. Okay, so we had basically used filters to narrow this data set down to where we had a pretty tight cloud, and then we applied the trend line feature of Excel to that cloud, and we have an equation that's basically going to let us predict kW as a function of outdoor air temperature. Couple things about that. Especially when you get with higher order polynomials, in other words, like a fourth or a fifth or a sixth order polynomial, then even though this is a little tiny number here, the number of decimal places can actually make a big difference in the results you get, because a little thing taken to a power becomes a very big thing. And so you always want to make sure you use, you set up the formula and format it so you have enough decimal places to give you good results. I usually go for two or three decimal for a decimal place setting that gives me two or three numbers at least ahead of the highest order exponent on x. And so this should be just fine. But if you wanted to make it have more or less decimals, there's a really complicated way to do that using a function called lineest, which is like, I actually did a blog post on that, because when I first discovered this, I was modeling a curve and I had a sixth order polynomial and I was using one decimal place, and the model didn't match the actual data, and I got curious about that, realized it was an exponent thing. I knew Excel must know these coefficients to more decimal places than I could see, and lineest lets you figure that out. But it turns out there's a very simple way to do it. Like if you click on that and you say format the trend line label, which automatically showed up over here for me since I had the format feature open. But if I sort of right clicked over it and said format trend line label, same box would open up. And I pick the number category and I put it to number. Now you'll notice I can control how many decimal places. So I can make it 4. And now I got 4 decimal places. I could make it 10 if I wanted to. Now I got 10 decimal places, which is more than I probably need. There's a point of diminishing returns on that, and I'll actually show you that later in an example. But I'm just going to keep this at 4. Okay. So how would you use this equation to predict energy consumption? It's actually not that hard. Basically, you need some source of weather data for a year. Now, there's a number of ways you could do that. And matter of fact, I'm just going to pop a couple slides open here because I got the links in them. I'm going to put these slides into the post, the blog post. So you'll have them that way. But one way is, I mentioned this earlier and we looked at it. Bill Coran has a tool that lets you go out and query an ASOS site and basically bring back even more than a year if you wanted of hourly data. Another source is the National Weather Service, and I have a whole bunch of different blog posts that talk about different ways to do that. If you go to my blog and go over here and pick the weather and climate resources, all those posts will come up. Now those two sources would give you data for an actual year, and a lot of times when you're sort of projecting, you'd rather use a normalized year. That's and one example of a normalized weather data file is called a TMY file, typical meteorological year file. And it turns out a lot of the electronic psych charts that are out there actually have TMY files built into them. You can go find them online too. But if you happen to have Acton psych chart, and it turns out the company that make Acton actually makes a lot of the electronic psych charts, including the ASHRAE psych chart. The ASHRAE psych chart's actually Acton psych chart, or vice versa. And in particular, the GreenX psych chart if you go to GreenX website, which is what the link on that slide was about, and again, those slides will show up in the, or those resources will show up in the actual blog post. If you go to GreenX website, they offer a free electronic cycle chart that'll do basic things. You can plot points, read values off it, and stuff like that. You can upgrade it for about $70 to the Pro version, and the Pro version has the TMY files in it and stuff like that. It's basically a subset of Acton. It's the Acton cycle chart sort of focused on HVAC. So it's actually a very good value. And so, basically, when I say it has a TMY file built into it, if you hit analysis and say open a weather data file, you get a menu like this. And the project we're looking at is in Atlanta, and I happen to have picked that. But you basically pick your state, pick your airport, and you pick a bin data plot if you want to see it on the cycle chart. And so what this is going to do is it's going to plot squares that are 2 degrees dry bulb horizontally by 5 grains per pound of moisture vertically in different colors, and the colors are going to tell you how many hours per year tend to occur in those squares. So basically it's probably easier to just show you this. So I picked a bin plot and I'm going to say apply, and so now this is basically a picture of the Atlanta climate painted on the cycle chart. And what it means is where the red square is right here, it basically means there's 105 to 117 hours a year at that condition. There's 91 to 79 hours at this condition. Any of the squares that are sort of this lime color, there's 52 to 40 hours a year. And these darker blue squares, those are the conditions that have the least hours per year. So that's bin weather data plotted on a cycle chart. You can also, if I go back to that little menu there, notice I can click data table, and I can say text or comma separated value. I'm going to pick comma separated value because Excel likes that better. And I can say create a data table. And when I do that, it says I'm going to save this in a directory on your root of your C drive, just so you know. Say OK. And basically what it's doing is it generated an Excel file which it opened. So here is an export of the data behind that plot. I'm just going to highlight all the rows, and you'll notice basically it has it by month, day, and hour of the day, dry bulb, wet bulb, dew point. And so these are the normalized data over a period of years for Atlanta, Georgia. The difference between a normalized year and an actual year is a normalized year will smooth out all the bumps from extreme days. And so if you're just trying to get a general picture of what's likely to happen year after year after year, you're probably better off using a normalized weather data file. If you're trying to understand how your building responded on a particular year or to a particular event, like an extremely hot day, a day above design, then you want to use the actual weather data. Or if you want to project how it might react to an extreme day, you want to use the actual weather data. Okay. Now, to use this, I usually just create this data and just move it into the spreadsheet. So if I go on this tab and I right click and I say move or copy, I just want to move it, and I'm going to move it into the workbook we're working with. So I'm going to put it in this workbook and make it the last sheet in the workbook. So okay. So now you'll notice that tab is now embedded in this workbook, which will just make it easier for us to work with it a little bit. So a couple things. Excuse me. This data, basically, as I recall, this is Nick's data for Nick's chiller plant, and it runs from the 1st of January 2015 through the end of July 2015. And I'm suggesting that we can use this data and the equation of this line to project how much energy the plant had used for a whole year, even though this is only half a year's worth of data. Now, how good a projection that's going to be is going to be a function of, how broad a temperature span do I have to look at. For instance, it looks like I have data all the way up into the high 80s and all the way down into the low 30s. And so how much of Atlanta's climate is represented by those temperatures is the question. And we'll look at that in just a second. This is probably a pretty good data set compared to, say I just had data and it was for all the days that the data happened were 85 to 90 degrees. And so I might still project some sort of curve, but the curve's only based on data in this region, so it's not nearly as good as having data over a broad span. And so a couple things about that. If you're going into a building and you're trying to understand how it worked, you might want to look at a normal day and extreme days, and what I'm about to show you is a way to find those days. Or if you're going to log data and you can capture a data string that happens to have days in it that see the entire, or a significant part of the temperature span for an entire year, and you just happen to do it in a week because it's a swing season, that's going to give you data that's pretty useful to project the entire year, versus you're there in the peak of summer and so all week it's between 70 and 90. That'll tell you a lot about how the building works then, but projecting what that building's going to do when it's 30 off data that you captured when it's 70, 80, 90 degrees isn't going to be as good as projecting what the building will do when it's 30 off of a data set that you captured when the building saw conditions that went from, say, the mid 40s up into the mid 70s. Okay, now to get a sense of that kind of thing, one of my favorite resources, and I have this saved, and I actually show you how to get to this resource off my blog and those posts about weather and climate data. But like if you go, basically just go to the National Weather Service. If you go to the National Weather Service homepage, and from that location type in the zip code you're in. So I'm going to type in Portland 97203. Or you could type in Portland, Oregon, or you can just pick that and you say go. It's going to take you to the current forecast for Portland, which is interesting and all that, but what you're really looking for is where's the local forecast office, which will show up in this, right up here. If you go to the local forecast office, and the specifics of this will vary from region to region, what you're looking for is the climate data graphs, okay? And so most of the regions, but not all of the regions at this point, have them. Typically, if you go to the local forecast office's home page, you'll discover them down here on the home page someplace. And so if I click on that icon there, it takes me to a page that basically has these cool little charts. And what's cool about these charts, I'm going to make one bigger so you can see it. Basically, these charts have sort of four pieces of information. The fuzzy light blue bands, those are the extreme cold days on record for Portland, Oregon, basically specifically the airport weather station, in the month of August. The reds are the extreme hot days on record for the month of August. The green is the normal band, in other words, that statistical TMY file-like band of weather. What's it normally like in Portland in August? Well, it's sort of that green band. And then these dark blue bands are what actually happened this year on those days. In other words, we had some really hot weather here in Portland for us in the month of August. We hit or exceeded extremes. There's a similar graph that shows, precipitation, the record, and what actually happened. So you can look at them, you can go back and you can sort of eyeball those nomographs. You can go back several years. And kind of what I'm looking for is, I'm looking for a day in the cold seasons where I got down to an extreme low. I'm looking for a day in the hot seasons when I got up to an extreme high, like where's August? Like that day in August, Portland was high. And then I'm looking for a day that has a really big swing in it, because that basically exercises the building. In other words, if we go to this graph for a minute, not only would this particular, if I looked at data from, what is that, July 1st, 2014, if I looked at data from that day, not only would I see the systems exercised, in other words, went through a pretty big temperature swing, all the way from the upper 50s into the, over 100. So 50-degree temperature swing, that's a pretty significant thing for a system to have to deal with. But I also would see how the systems reacted on a near record high day. That would be a very useful day to look at data from the building. And so if they had trends running and you could get trend data for that day, it would tell you a lot. Okay. If you go back to the temperature graphs page, there's a yearly charts option. And the yearly chart just puts all that stuff together. And so this lets you, like in one fell swoop, look at what the climate for Portland's like. And so if you happen to log data in Portland and you happen to hit a week like maybe right in here, let's look at that day in 2014 in July. If you were logging data on that day, you actually saw a pretty good span of the temperatures we'd typically see in Portland. So projecting annual consumption from data for that day or data from the couple weeks and around there would be a much better result than, for instance, if all you had was logged data for these couple days, where it did vary 10 or 15 degrees, it was in the 40s, but it really doesn't tell you much about what's going on here. So the point is, this helps us understand how good our data set might be for predicting the year. So if I go look for the same thing for Atlanta, which I happen to have saved, Atlanta, it can be down in the, normally in the upper 30s. Extremes can actually be to the zeros, and the highs can be in the upper hundreds. If we go back to our data set now, we have temperatures as low as 11 and as high as 96. So our data set, even though it's half a year, represents the building's experience over conditions that cover pretty much the spectrum of what you see in Atlanta. So this is probably going to be a reasonable way to predict. You'll feel pretty comfortable with this versus, say, our maximum and minimum were 65 and 85. You could still predict from that, but it wouldn't be as firm as something built off of actual weather data with a broader span. So that's all I'm really trying to say. So let's see if we can use our equation to predict how much energy the building will use for a year using this weather data file. And so all we really need to do is we have an equation here that says here's the y kW as a function of x, outdoor air temperature. And so I'm just going to copy that equation so I can use the parameters in this other tab. So I'm going to go over into this tab and I'm going to paste my equation in right here just so I have it to reference. I'm just going to paste the text to keep the formatting. Okay, so there's my equation. So now I'm going to add a column here. This is going to be projected energy use based on curve fit equation. Okay, so and the curve fit equation, if we want to stick it in there, I'm a big fan of making sure everybody understands what you're doing. So I'm going to take this equation and I'm going to add it to that title. And actually I'll put it here. And I'm going to put the terms we're interested in. We're basically saying the kW, which is y, is equal to 0.0496, and this looks like a time symbol. It actually represents x squared. So I'm going to say, and x is outdoor air temperature. So I'm going to say times OAT for outdoor air temperature squared. And if I want that to actually show up as a little superscript, if I highlight it and then go to font and say superscript, when I get done here, it'll actually show up as a, well, you can see it happened already. So if you watch over here, now it says the KW is equal to, you know, 0.0496 times x squared minus 7 times x, which is outdoor air temperature. So I'm using the x as a time symbol, and I'm putting OAT in, which is what x is, plus an intercept of 0.379 or 371.9275. Okay, so that's the equation. So I want to just basically plug that equation into this cell. So I want to calculate KW, and since these are our intervals, I'm actually, I'm taking KW, which is a demand, but KW for an hour is a KWH. So this is KW and KWH in a way. So basically the equation I want to put in here is, and I'm going to, just to make it easier on myself, copy these so I don't have to type them. So I'm going to go into the cell. I'm going to say equal, put some spaces in because this is just for me to copy and paste. So the equation I want to do is I want to say the KW is equal to, and I'm going to use some parentheses to keep my terms collected. The KW is equal to the outdoor air temperature times, oh, I'm sorry, the KW is equal to this, that number right there, times the outdoor air temperature, which is this cell, squared. And the way you square something in Excel formulas is use the up arrow to indicate it's an exponent, and then I want to square it. So basically that's our first number in our equation, and then we're going to going to say, from that we're going to subtract, I guess is what I'm trying to say, this number times the outdoor air temperature, and then we're basically going to add the intercept. And now I want to get rid of this because I was just using that to make it easy to cut and paste. So if I did that right, yeah, so now we have an equation that basically is projecting 120 kW for this hour. And so if we just copy that equation all the way to the bottom of this file, and I'm just using the same techniques I've been using before to do that. So now for each hour we've calculated the KW. I doubt if we've calculated it to 4 decimal places, so let's just be real here. In fact, let's format this as a number to 0 decimal places with a comma separator. Okay, so basically we now have the projected KW consumption for each hour of the year, and so if I add that up, that's how many kilowatt hours we think that base load will use in a year for that facility. So if I basically say equals, and I'm going to use another function here because I want to be able to, I'm going to filter this. What we're going to do is see what it projects for the year, and then we're going to see what it projects through the end of July and compare that to what the plan actually used, just to see how good our projection is. So what I'd like is I'd like to have a sum here that automatically updates itself when filters are on, and that feature is called auto sum. And so if you go to formulas and see auto sum and you push that, and basically I should have done that differently. I'm going to highlight this range. So I'm going to highlight that, and I'm going to go back to the bottom of it. And there's other ways. You could just type in auto sum also, but I'm going to click in here. And it didn't work the way I wanted to. Anyway, let's just do this. I'm going to say auto sum, and I need to tell this a little bit more information. Sorry, I'm going to do this a different way. I'm so used to doing, oh, I know, I haven't filtered it, that's why it's not auto summon. So let's just go ahead and do what I just did, and then I'll show you. Okay. Okay, so now let's put that in there for me. Okay, so basically we're projecting that the building is going to use a little over 1 million kilowatts in base load for, like I said, I believe that was Nick's chiller plant KW, in the course of a year, based off of our analysis and our equation that we developed from about 7 months of data. So now let's filter out everything after July, see what the total is, and compare that to the actual total. In other words, what Nick actually saw. So let's put a filter on here. So go back to data, filter, and basically I want to get rid of August, December. I want to keep February and January, July, June, March, May. I want to get rid of November, October, and September. September, October, November, December, and August. Yeah, I've unchecked those. So now I've filtered this data set down. When I go down here, yeah, it stops at the end of July. And now here's where the auto sum comes in handy. If I click back in here and say formulas, auto sum, notice it changed the formula a little bit. It kept the same range, but it added a parameter up here, 9. And 9 basically means sum everything in the column, but don't sum the hidden rows, just sum the rows that are visible. So since, you'll notice here, after July, there's a bunch of hidden rows. We don't want to include the rows that are hidden in our total. We just want the rows through July. And so our model says the building, or the base load consumption will be in the 600,000 kWh range based on our model. Let's look at what the actual sum was. And so again, these are kWs for an hour. So if I go down to the bottom of this and I do the same auto sum thing, I have a slightly different number, but there's, I think, a reason for that, because we restricted the hours, and there we just restricted the months, but here we also have hours restricted, so we need to go filter that other spreadsheet just a little bit more. I'm going to format this. So this is a different number than that, obviously, but here so far we only filtered out the days after July, and you'll recall here we had also filtered out a bunch of hours. Specifically, you can tell where you have filters applied because the little drop down thing changes to a filter shape. If I click on that, we basically have filtered out all the hours between 2 in the morning and 10 at night, or 8 at night. 9, 10, yeah. So let's go make that same filter on the weather data file. Which I think we can do. Yeah, we want to filter out hours. So we basically want to get rid of 10 to 11, 11 to noon, 11 to midnight we want to keep, noon to 1, no, we want to keep that. We want to get rid of that. 1 a.m. to 2 a.m. we want to keep. We want to get rid of that. I think we kept, 2 in the morning, 3 in the morning, 3 and 4. Okay, so I think basically we've filtered out 1, 2, 3, 4. 1, 2, 3, 4. So let's do that. And let's go back and make sure we've matched up. Oh, we want to keep those hours, We want to take out everything but 1 and 2, 0 to 1, 1 to 2, and then midnight to 11, 11 to 10, 10 to 9. So I did it backwards. So let's go back here. Select all. So I'm going to keep everything but. So we don't want that. We don't want that. We want that. We don't want that. We do want that. We don't want that. Okay, so now I think we have a match. So we filter it for that. And let's see if our totals are closer now. Yeah, so now, the model projection using a TMY file comes up to like 132,000 hours a year, and the actual consumption for the year so far for Nick for this was 111,978. And so if we just look at that in terms of percentages, it's probably within 10 or 15%. So if we say this is equal to that divided by that, format as a percentage. Yeah, we're within, I guess, 18%. So not bad, considering, this is a normalized year, this is a real year. Oops, sorry. This is a real year. We've not seen the entire swing of temperatures that you'll see in a complete year. So that's my point, I guess, is that by using a technique like this, where we develop the scatter plot and then applying filters to the scatter plot, we can narrow the data set down to where we can get a pretty good curve fit. And then we can use that curve to project things like annual energy consumption based on a smaller data set. And it's very powerful. There's a bunch of ways you can do that, a bunch of other things you can do with that I'm going to sort of illustrate with slides and screenshots of slides in the rest of the post. And so I think that's pretty much what I needed to show you. I'm going to make one more quick little video clip to show you how to use VLOOKUP. I mentioned that Nick had used VLOOKUP to associate an outdoor air temperature with each one of his dates, since he didn't have that data. And so I'll make a little video clip to show that, and then that'll be it.